All right. Good evening, everyone, and happy new month to you all. My name is Gloria. Welcome to our Light Methods today. This is Java user group. So today, I won't be wasting much of your time. We'll be talking on the topic Java concurrency, an overview of that. But before I invite the speaker, just in case you're here and you're yet to join our community, please be keeping your eyes on the chat box. I'll be dropping our social handles so you can join or share to your friends as well. So our guest speaker today is Mr. Ebube, also a Java JUG member, NAIJA-JUG member. So I know it's going to be an interesting one. Just stay put, learn and unlearn. But please, before the speaker take over the mic, you know our routine. Please, could we react to our favorite emoji to show that we are ready and we are waiting to digest what we have tonight. Precious, thank you very much. Moshood. Okay, Kingsley, Taiwo is not clapping. Marvis, I can see you. Look, man, thank you. All right, if we can have the floor, I think a lot, the percentage that are waiting are much. John, thank you very much. You can have the floor.
All right, good evening, everyone. My name is Ibube as the as already stated. Okay, so we're going to give talking about Java concurrency and concurrency in general. So we're going to have an overview of the available options that Java provides you with. So it's not going to be a deep dive into any one model or any one use case. It's just going to talk about the different options and the different use cases and where they tend to be used in practice. As even also talk about the new Java virtual threads project Loom, which is stable in Java 21 and modern versions. Okay, so you can see the overview here already. Please confirm if you can do like with reactions. So first of all, we're going to be having a definition of concurrency versus parallelism, types of concurrency. Yeah, and then the normal data structures that you use to prevent data races. Then we're also going to have a brief overview of CompletableFutures and async in Java, which you don't really tend to hear about or tend to see because of how complicated it tends to get. So, okay, first of all, concurrency. So a simple definition, concurrency is just the ability for a computer to handle multiple tasks at the same time. And the reason concurrency was so important was that in the early days of computing, when the first computers came around, you had something called time sharing because computers were very expensive. Only a few people had access to them. So then you had so they needed a way, because computers were faster at doing things than human beings. So they needed a way to make efficient use of the CPU. Because rather than having the CPU being idle, you wanted to do as many things that it could as possible. So before operating systems became mainstreams, the normal mainframe systems where you would have different users plugged in to one particular computer, the mainframe computer, it would be handling each of their requests concurrently. Let's say when it's doing something for one user that requires waiting, it will quickly switch and handle another user's request. So concurrency has always been like a hot topic in computer science and also in programming. So again, concurrency is different from parallelism, as we're going to see. Like it's a very, very hot debate. People tend to confuse the two. So hopefully at the end of this session, you at least know the difference, if not for anything. So again, want to make efficient use of the CPU of computers because they are very, very fast, and we want to make sure like at no point in time the CPU is idle. So we always want to make sure our CPU is working because they are very, very fast. Okay, so it's also useful for things like in UI design now, like when you're designing user interface applications, because you would have like, if you just had like the computer doing one thing, just rendering text on the screen or displaying the user interface, it wouldn't be able to do multiple things at the same times. Okay, so again, concurrency, it's not parallelism. I am guessing from the image, you'll be able to tell the difference. So concurrency is the computer switching between two different or multiple tasks. It's quickly switching between it, but it's now giving the illusion that it's doing both of them at the same time, but in fact, it's not. Concurrency was what you had for a very long time because before computers became more cheaper and more widely available, you only had one CPU core. So there was only one core of the CPU processing requests at a particular time. So it was not possible for parallelism to happen. So what you had was that the computer quickly take one request, one stop it, switch to the other one. And it was doing this thing very, very fast. If only when it knows to stop a particular process and start another one, it honestly depends on the implementation of the operating system. So some do first in, first out. Some try to make it as fair as possible between different processes. Then other operating systems tend to use a mix. So it really depends on the goal of that particular operating system. But in parallelism now is when you now have multiple CPU cores, as we tend to do today in the modern world. So in this one now, you actually have like two or more requests being processed at the exact same time, because now there are multiple CPU cores, not just one. So you can be processing multiple requests at the same time rather than just switching. So, and what you tend to have is actually a mix between the two. So concurrency can also happen between multiple cores, and depending on like the operating system and what's happening, you actually tend to have a mix where sometimes it will switch between a task, sometimes it will be executing different threads at the same time across multiple cores. So the topic of concurrency is even more important than ever because now we have the tools, we have the hardware to run like multiple threads, multiple processes at the same time. So it's very important that we make efficient use of them. And Java provides us with certain APIs to do that. Okay, again, concurrency, handling multiple tasks, but switching between them. Parallelism is them running at the exact same time. A keynote is to know that parallelism tends to happen when you have multiple cores, because that's the only way to do two things at the same time, to share it. Okay, so traditional threads in Java. Okay, before we dive into the whole implementation, we have to understand what threads are. So your operating system provides one abstraction to represent a program running in memory, and that abstraction is called a process. The process tends to have like different information about the current running program, like where its code is stored, the amount of memory it needs, the virtual memory that the operating system creates for it, because it tends to like, it creates virtual memory like it will be using some parts of RAM and some parts of the disk, and to create an abstraction so that each running program thinks it is the only thing running on your machine. So there's this form of isolation where each program running on your operating system thinks it's the only phone. Then within the abstraction now called a process, you have what is called a thread. So the simplest way to think of a thread is that a thread is just basically like one unit of your program's instruction, or a process instruction running at a particular time. So and the definitions tend to vary because honestly it depends on the particular operating system you're using and the particular tasks happening at the same time. But the best way to just think of it, just think of thread as a particular instruction running or a particular task in a process running at a particular time. So again, you have your operating system managing different processes. Processes are just the abstraction for each program. And within a program, you have one or multiple threads. And remember, a thread is just like a task in a particular program that is running at that particular time. So Java provides us with a raw thread API to access operating system threads. Now, in the world of programming, there are usually two main types of threads. Raw operating system threads, which tend to be more costly to use, and then what you call virtual or green threads, which tend to be managed by a particular runtime. So for a long time, what Java used was the raw operating system thread. In fact, like if you're using anything below, I think it was Java 17 when virtual threads came about, what you tend to see is just raw operating system threads. So like what you get was like it was very, very easy because like you didn't need to have like a separate runtime managing, separate user threads. So it was very, very easy to just plug and play with each operating system. But like the downside was that the high memory, because like for each thread now, like I said, for each process now, the first abstraction your operating system will create for a program is called a process, and it needs to store information about it. I don't do it like deep into the computer science, but like it will store information like where it stopped, like the particular instruction it was running before it paused it and moved to another program, and so that like the stack pointer, the program pointer, and other variables like that. So for the abstraction of a thread, memory also needs to be allocated for like each particular thread, because apart from switching between processes, the operating system will also switch between threads. So it will tend to store like that particular thread context. So like when it comes back to it, it will know where it stops and continue from there. So it tends to be high now because again, you need to store the program, where it is in memory, the particular instruction, the pointer to the particular instruction, where the pointer to the particular stack, and the variables that are being loaded in memory, the variables that are on the stack, the variables that it's allocated on the heap before switching. So there was a high cost of memory. So, but that was the raw API. So the code example shows a basic way of running a thread. It's important to know that Java is multi-threaded compared to, that just basically means that any program you write in Java will be able to run we're able to have multiple threads of itself running, compared to other programs like JavaScript or Python that are single-threaded. So you only have one thread interpreting your program's code. But in Java, you can have like the program's instruction being interpreted in multiple threads. So concurrency could happen, at least the basic form of concurrency. So Java provided an executor framework, which was an abstraction over raw threads. Now, if you're wondering why like we needed an abstraction over like raw threads, why don't we use raw thread? Because like I said, creating a thread was very costly because it was being managed by the operating system. And then, okay, you can't create infinite because you run out of memory. And even if you don't run out of memory, it will be very, very inefficient. So what most programming languages tended to do was to have something called a thread pool, which is just basically a group of threads that are available for work. So again, it was basically a group of threads available for work. That was called thread pooling. So rather than you just having people just access raw threads and creating as many as they like, Java used the executor framework to provide a thread pool, which is just like a group of threads are available for work now. And so even if you were to call multiple threads, it should just be taken from one pool. So if we were to call 500 now, and okay, in this code example now, we're creating a fixed thread pool of 4. So we only have 4 threads in this pool. So if we were to create a program now that was doing something like 100 threads, if the 100 tasks will just be shared between the 4 threads. So once one finishes this thing, it will move on to the second one. So this allowed programs to not like abuse memory. So you don't run out of memory and your programs don't hang, or worse, your operating system doesn't just kill your program because it's consuming too much memory. Yeah, so that was the whole point of the executor framework, and that's what most people use for a long time. Now, it's important to realize that the thing with another issue with operating system threads was that the implementation most people tended to use was blocking. So yes, with threads you can do multiple things at the same time in your code, but if the problem was that, okay, now, let's say you have two threads now. One is rendering your UI. So one is rendering your UI. Even in the old days of Java applets, now when Java was meant to run on the browser, so one is rendering the UI and doing small dynamic rendering in the front end. Then you now have another background thread now fetching something for the data. Let's say you really had two threads, two operating system threads allocated now. So once that thread now is now like requested for data over a network, it's now going to block because that thread is now not going, it's not going to do anything. So it's just going to wait until it sends like an interrupt to be notified that, okay, the data you requested for is back. So now you're not having that efficient use of the CPU now because you have a thread that is being idle and you can't even create like a high number of threads in the first place now. So most implementations people tended to use was blocking in the executor framework. Now, okay, you also have the problem of, okay, now you now have different units of my code running at the exact same time. What if they needed to pass data between them? The two main models that tend to be used in programming is either they share some memory, so two threads will share some memory, or they will pass messages between each other using either raw sockets or channels, like you tend to see. So, but the one that was the one that is more popular in Java is sharing memory, which is discouraged now in modern practice, but it still has its uses. Still, like, again, you share memory now. So again, the problem with sharing memory is that now, okay, you now have like a memory space that can be accessed by different threads. So it's possible to have what we know as race conditions now, where two threads are trying to change the exact same memory space at the same time. So this can lead to inconsistency. So then you now have synchronization. Synchronization was the way like to prevent race conditions now. So in C, the first one you have was like a mutual exclusion data structure. Or in mutex, the whole point was in mutex was just to allow only one thread to access a particular resource at a particular time. And the idea was that the thread will hold what is called a lock. So as long as one thread holds that lock, only that thread can access that particular resource until it unlocks it, and then another thread now holds the lock, locks it until it's done with the resource, then unlocks it. But the problem with this is that you now have, like, you stop having concurrency now, because now you have multiple threads, but they need to wait on each other. They can't like access it at the same time. So that was the trade-off you had it with mutexes. You also have what was called semaphores. But semaphores, just like mutexes, but you can now have multiple threads, like holding the locks to a particular memory space or to a particular variable, but the same downside. So you now had atomic classes now that provided lock-free operations. Now the idea was that you would it was another form of concurrency. Well, the idea was that like you perform a particular operation as a single atomic unit. So like it's like abstracted the whole locking and unlocking into like just one particular transaction. That is what transaction. Just one particular operation. So rather than you doing like in the code example, rather than you first locking the particular operation you want to happen, then remembering to unlock it when you are done so the other threads can access it and you don't have blocking code. The atomic classes provided an abstraction, so you just have everything happen instantly, like it to give the abstraction of it happening as a single operation now. So it was a more programmer friendly feature. But again, the problem with all these other ways is that they are still blocking. Even with the atomic classes and the abstraction it provides, it was still blocking on that hood because each thread had to wait for one thread to finish doing whatever I wanted before it got the data. Or if we had network calls now, or situations where the CPU is performing one CPU intensive task, you still have blocking code now. Okay, now it's important to note that there are two main places where you'd want your code not to block. The first one is when your CPU is idle. like when a thread is not really doing anything. So, and the second one is when the operation that the thread is going to run is going to take a very long time. So those are the two main places you don't want your code to block. But the first instance now, when your thread is not doing anything, like I said, when you do an IO operation, either over a network or you're reading a file, that's basically a system call. Like it's not your thread that's doing it. It has to wait for the operating system to like take control into kernel space and then notify it that, okay, this operation is done. The data you asked for is now loaded into memory. So that time that it's waiting for that interrupt signal, it can be doing something else. So you don't want your code to block then. So that was the idea of asynchronous programming, where you don't have a form of cooperative concurrency, where you'd manually or explicitly like tell your code, okay, once you reach this place, start doing something else, or just wait for the results. So now you have a completable feature. It's just like what's the word, features or promises rather, sorry, in JavaScript, where you have a promise of the data that you wanted to access over a network. Now, the second instance where you don't want your code to block is when you are performing an operation that is going to take a very, very long time. Now, okay, let's say you have it. Let's imagine Java was single-threaded like JavaScript now, and we can spawn multiple threads now. And now we want to encrypt a user's password using one of these modern algorithms that tends to take CPU time. So now, rather than if we just to like have one thread now and do it in a blocking way, the UI is not going to render now. The user, if the user starts clicking on something else, nothing would happen because your thread is still trying to run. Your CPU is still running the encryption algorithm to encrypt the user's password. So now, like what we ideal to happen, since that kind of thing will take a long time, was that you want the CPU basically to execute small part of the algorithm, then quickly update the UI, then switch back, execute another part of the encryption algorithm, then switch back, update the UI. So it's giving the user feedback on what's happening. So everything doesn't just block. So that's the whole idea of asynchronous programming. And the good thing about asynchronous programming is that it's very, very sweet when you have like a single core. In fact, that was like what many languages were doing back then. When you just have single cores and you can all like spawn multiple threads. Because then you even if you're not able to spawn multiple threads, you're able to like explicitly have control of when your code is going to block and when it's not going to block. Because when you have a blocking operation, you can just suspend it. Here you can see where isn't the supply keyword. Well, don't focus too much on the code because CompletableFuture they are still very, very confusing. Like hopefully in the future we can go into them. So they don't tend to be used as much. In fact, like in modern in Java applications like in Spring Boot, what you'll be seeing mostly are abstractions over the completable features or just raw threads being used because of how complicated the API is. So again, asynchronous programming, you don't want a particular thread to block either when it's making an IO operation where the thread is idle or when it's going to do a CPU intensive task that it would be better, more user friendly for the CPU to switch between doing one task and doing another thing rather than just have that long running operation run. It's better to just switch. A use case is updating UI and running an encryption algorithm. Okay, now in Java 21, it was before Java 21. I think it was in Java 17. They released the first virtual threads in Java. Okay, so I feel like there were two main ways that threads tend to get implemented in programming languages. They are what is known as green threads or virtual threads or lightweight threads, and then raw operating system threads. The main difference is that in raw threads, the thread is being managed, the memory, all the information about the thread that it needs to run is being managed by the operating system. So those tend to be more costly. Like in Java applications, you see like over 1 megabytes or more, depending on the operating system and the JDK version you used, tended to be allocated. So you can't just spawn many. But with lightweight threads now, the threads are being managed by the runtime. Like an example of this that is very, very popular are Go routines in Golang, where it's managed by the Go runtime. The Go runtime is compiled into each binary application you build with it. So the same thing with Java. So basically, the whole idea was that they build an executor and a scheduler, sorry, build an executor and a scheduler to manage when this lightweight threads were run. And in a way, it solved both the need for, it solved both the problems that we had with classic OS threads that were very memory heavy, and also completable features where we wanted our code to be non-blocking. And the idea is this: since you can have many lightweight threads, you can spawn many. You no longer need to have a thread pool. Like you no longer need to assign, okay, I don't have much memory on this my server. Let me just make a thread pool of 4. Or let me just make a thread pool of 5. You no longer need to do that because you can spawn because of how light they were. I think they are about, if I remember correctly, I could be wrong, please correct me if I'm wrong. It was about 20 kilobytes of stack data per thread in the Java. In Golang, it's 2 kilobytes. In Java, I think it's 20. So you can, because of how light they are now compared to 1 megabyte, you can run many of them. And what the Java scheduler tends to do is that once it sees that a thread is idle, it will just automatically schedule another thread to run. So under the hood, all these, so let's say you're running like 1,000 virtual threads. Each of these is being mapped to a real operating system thread. And like I said, what tends to happen is that sometimes threads are idle. And so the scheduler, it to map each of the virtual thread into like operating system threads, and it's now be assigning it. So like you can have like 2 threads sharing like one particular operating system thread, and it should just be switching its. So the scheduler will be switching between each virtual thread, while the CPU is just basically in the CPU's mind is just basically running one thread. I wish I had like an illustration to show you, but just think of if you have seen someone weaving mats where you'd have multiple multiple threads of the mats, but it's not being woven into one single one. Just think of it that way, where you have multiple virtual threads. Then the Java runtime, the schedule in the Java runtime is basically weaving each of them into one single operating system thread. So in this CPU's mind, it's just running like one OS thread. But what's happening is that the Java runtime is switching between multiple virtual threads. So it's all about the idea of blocking codes now. So if you had a virtual thread that was blocking, let's say you assign a virtual thread now to basically fetch data from a network, and okay, it's done that, it's waiting for the data to come back. The scheduler will see, okay, this thread is idle. It will just basically switch, give more CPU time to another virtual thread. So now there was no longer, at least there is no longer any need most of the time to use completable features. So for a very long time, Java developers were now happy. Okay, so Spring Boot and concurrency, this is just a very, very, I'm not even very sure if this code is even correct. But in Spring Boot, you had the async keyword, and you also had what was called reactive programming in Spring Boot, which honestly was very, very complex. It's still very, very complex. But like I said, with virtual threads now, nobody has to suffer again. Nobody has to cry. Rather than using completable features or reactive programming or webflows in Spring Boot, you can just use virtual threads. And you know that once that thread blocks, the scheduler is just basically going to schedule another virtual thread to run. So your code is almost non-blocking. So modern Spring Boot applications tend to favor virtual threads over anything like reactive programming or normal completable features using the raw API. But in very, very niche use cases, they still have their uses. So it's not as if we are going to do away with them. We just pretty good that we never have to write it ourselves. Okay, again, JavaFX concurrency. If you where in the early days of Java, when all of us were still using Swing, you'd know that like the Swing UI, the thread that updates the Swing UI, like runs in a separate thread. It doesn't run in the main thread that executes your code because it was not memory safe. Spring controls, like that's the UI controls, are not memory safe. So you cannot have multiple threads accessing, mutating the UI at the same time. In JavaFX, they solved that concurrency issues more, which is one of the many reasons why JavaFX is superior to Swing. So that's another use case of Java concurrency. They also benefit from virtual threads again, because you also have almost non-blocking code in the same thing. So you don't have your UI freezing, and you don't need to use CompletableFuture's API. Okay, now Android and Kotlin. This is just a bonus, but Kotlin took a very different approach when they were trying to solve the issue of concurrency. Because when Kotlin came out, the idea was to replace Java in developing Android applications. So they decided to use cooperative concurrency. Java uses what's known as preemptive concurrency, same as Golang. The idea is that the thread your program doesn't have a say-so of when it's going to give up control. It thread doesn't have a say-so of when it's going to give up control. It's the scheduler that does it automatically. So the scheduler just looks at, okay, this thread is not doing anything, or this operation is going to take a long time. Let me just quickly switch to something else. That was preemptive concurrency. So preemptive concurrency is sweet because you don't have to manually manage the thing yourself. You don't have to manually manage, okay, suspend this task here, go and do this other one. But the downside is rather you only use it. It tends to be more preferable when you have like more memory. And in the old days of Android, phones didn't have as much memory as servers and large computers. So Kotlin uses cooperative concurrency. In cooperative concurrency now, you're basically explicitly stating where each lightweight task will suspend. That's basically what you have in tools like JavaScript now. Because again, browsers were so yeah, basically telling like each task when to stop and do something else. So it was a more manual approach. It was not as like hands-free, as magical as you have in virtual threads today, where you're just spawning threads anyhow you like, and you don't have to handle whether they block or not. So, but they're not as efficient like in memory cases. So early Android phones didn't have as much memory as computers. But now that's different, sure. So Kotlin uses cooperative concurrency. So each task now was now lightweight, more efficient. So rather than spawn a new virtual thread for each thing without securing the world, you would explicitly handle each situation. Like modern Kotlin now, I think they are changing it, sure, since phones have more memory, but I'm not sure. I don't write Kotlin. Okay, so we are coming to an end of our talk. So hopefully most of you have questions. So key takeaways: concurrency is not parallelism, but most of the time you hear parallelism. What is parallelism being stated as concurrency? Just keep in mind that parallelism, they are happening at the exact same time, usually done with multiple CPU cores or CPU units. But concurrency, it's rapidly switching between each operation, giving the illusion of the thing happening at the exact same time because of how fast computers are. Again, Java provides an executor framework. So for those of you still unfortunate to be using older versions of Java that cannot migrate to newer versions, you still have to use raw threads. You still have to use threads, sorry, and you're obviously going to prefer the executor framework over raw threads because it gives you a thread pool and an API to easily manage them. Okay, you prevent race conditions with locks and atomics. Now, it's not as if race conditions cannot still happen just because you have locks. Apart from race conditions, you now have what are known as deadlocks. But this is another overview, so we don't need to go deep into that. Then CompletableFuture API enables asynchronous programming in Java. So if you're using raw operating system threads and you have an operating system, you have an operation that would either have to wait, so the thread is now idle, wait for a network call or for a file read, IO operation, or you have a CPU intensive task that's going to take a very long time, and it makes more sense to be switching between that thread and other threads. So you can be giving feedback and be doing something else rather than just have everything blocked on that particular operation. So Java provides the CompletableFuture API. Then virtual threads simplify both the need of using operating system threads and using the CompletableFuture API, because now you can spawn very, very lightweight threads that are now managed by the Java runtime, not your operating system. And then you have a scheduler in the runtime that when it sees a thread is idle or is taking too long, it automatically switches to another lightweight thread. So you no longer, most of the time, you no longer have to deal with the raw Futures API yourself. So that's going to be all for my talk on the options in concurrency in Java. I'm sure I made mistakes, so please correct me. If you have any questions, ask. If you have anything to add. And so that's the end of my presentation. So over to you, Ms. Glory.
Hello, can anyone hear me?
I can.
Okay, yeah, thank you very much. Please, can we react to Tafura emoji? Appreciation, our guests for that wonderful section. It's only Precious that is clapping. Look, man. Was only Precious that was in the class? All right, thank you, everyone. Please, do you have any question at this moment? We thank you so much for that section. Really learned a lot. Do we have any question? Wait, I want to understand something. Is it that anytime Ebube take lightning talks, there is no question at all? So we will know that if Ebube is handling lightning section, we will not even give room for questions. I can remember what happened the last time, so I have to force this guy to, but it's fine. So in the absence of any other question, we wouldn't want to waste our time. This is one of the shortest lightning talks. So let's just call it a day. But before we call it a day, right? This Saturday we'll be having DSA section. Stay put. George will be the one anchoring the DSA for this week. Then there will be a surprise. This is just for those in this meeting. There will be a surprise for monthly section this month of March. So stay put. Keep your eyes fixed on the keep your eye fixed on the adverts, and then try to join the section early enough, right? Yeah. So in absence of any other question, thank you so much for making today a remarkable day, for joining the section. Really appreciate your time, and we believe you've added to the ones you know before now. So we'll be calling it a day here, and we'll be seeing you all on Saturday, same time, same station. Do have a lovely night ahead. Thank you, everyone. Thank you. Good night. I'm giving all of you my favorite emoji. Good night. All right. Good night, everyone. Everybody, thank you so much. Thank you.
Good night, everyone. Thank you.